It's a pleasure to introduce Zvika Brakerski as the next speaker, who will be talking about quantum garbled circuits.
And now I'm unmuted. Hi, everyone. I'm talking about quantum garbled circuits, and this is joint work with Henry Yuen. I'm going to start by talking about the notion of randomized encoding and its relation to a garbled circuit. And I think I'm going to turn off my video because I need the real estate for the, I guess I can't. For my slides. Yeah, good. So the notion of randomized encoding, this is sort of a very fundamental notion in cryptography, and I'm going to explain it using the example of the parity function. So this is just the XOR of n bits. And how do you normally compute this function? Well, we're just going to have a tree of XOR gates. I'm taking n equals 4 here. I'm sure you can extrapolate to the general case. And this tree has a depth log n. And now what I'm going to show you is how to encode this function. So how to compute a different function that captures, in some sense, the essence of the XOR function in a way that I will describe in a minute. So what we're going to do is the following. So for each wire of this XOR tree, I'm going to sample a random bit. So we have R1 up to R7. And then what I'm going to do is the following. So I'm going to take my inputs, X1 up to X4, and to each one of these inputs, I'm going to XOR the random bit that is adjacent to it. In addition to every other node in the graph that is represented by this circuit, I'm going to compute the XOR of all the randomness on the wires that are adjacent to this node. So we get a function here that I'm going to call f hat, and this is a function of the inputs x1 up to x4 and the randomness values r1 up to r7. Now, this function has multiple output bits. It has 8 output bits, actually, as opposed to just 1 output bit of the original XOR function. However, if you look at the depth of this function, this depth is constant. It's actually depth 2. And I claim that f hat captures the essence of the original XOR function f. And this is formalized by this notion of randomized encoding that was first sort of formally introduced by Appelbaum, Yishai, and Kushilevitz, but was implicit in cryptographic literature even decades before. So what we require is the following. So first of all, we want correctness or decodability of this encoding. So we want to be able, given the output of f hat, to recover the original output of the function f. And notice that in this case, this can be done fairly straightforwardly because the XOR of all of these 8 bits actually gives you the output of the XOR of just x1 up to x4. And you can see this just by seeing that each one of these randomizers appears exactly twice. So they're going to cancel out. Good. So if I give you the output of the randomized encoding, then I didn't harm you in any way. You can still recover the original output. But however, you also did not get any additional information in addition to the original output of the function. And this is formalized by the notion of simulation, which requires that given the output of the original function, so I just see the output, I don't know what the input is, I can sample from the distribution of randomized encoding that correspond to this input, even without knowing what the input was. So notice that the randomized encoding actually defines a distribution by just taking these R1 up to R7 to be uniform. And I want to be able to sample from this distribution. And notice that in this case, this is very easily possible because the distribution of these 8 bits is just uniform conditioned on their XOR being equal to this output. So I can simulate this exact distribution very easily if I just know the original output of f. However, we can sometimes consider even simulating with statistical or computational indistinguishability rather than perfect simulation, and this also makes sense. So this is the notion of randomized encoding, and I guess the question is why? Why would you want to do this? And first of all, I want to point out that just being a randomized encoding, just because a function is a randomized encoding, doesn't mean that it's better in any way than the original function. F itself is a randomized encoding of itself. So we need to have some other advantage of using a particular randomized encoding. In particular, you can see here that in some cases, the randomized encoding can have beneficial computational complexity properties. For example, here, it's a low depth function that encodes the original function. And this makes this notion very, very useful in cryptography because, well, cryptographically, it captures the essence of F potentially with low complexity. So just one example, in the context of secure computation, you don't need to know formally what it is, but just sort of intuitively think about trying to securely compute a function. If I'm able to securely compute the randomized encoding f hat, then just by definition, I also get a secure computation of the original F. This is because if I computed F hat, then I can apply the decoding and obtain the output of the original F. But on the other hand, the security was not harmed in any way because, well, just getting the output of the randomized encoding does not give me any additional information other than the output of F itself. And randomized encodings are very, very useful in many other contexts in cryptography and also in complexity theory. Unfortunately, I don't have time to go over it in more detail. What I do want to point out is some other useful properties that this randomized encoding has, which are going to be sort of desirable for us to achieve. One is this property called decomposability. So you notice here that the part of the randomized encoding that corresponds to each one of the input bits depends only on this one input bit and possibly on the randomness. So there's no part of the encoding that depends on more than one input bit at a time. And there's a big part of the encoding that actually doesn't depend on any of the inputs at all. And this is sometimes called the offline part. And this can be computed even before you know what the input is. So this distinction between encoding of each input bit separately and an offline part, this decomposability is a useful property. So I talked about randomized encoding, but the title of the paper is Garbled Circuits. So what is a garbled circuit? Well, I don't know that there's like a strict definition in the literature, but to me, a garbled circuit is a type of randomized encoding for a class of circuits such that the randomized encoding works in a gate-by-gate manner. So in order to encode a circuit, what we do is look at each gate sort of individually, look at the functionality of the gate and possibly well, I guess we need to look at the random tape, the randomness as well. And we produce sort of what's called a gate gadget that is the encoding of this particular gate. And then the total encoding is just going to be the collection of these gate gadgets, the encodings of each gate separately. And we showed here a garbled circuit for the XOR function, but actually you can do it, you can sort of come up with a more complicated scheme with more than just one random bit per wire, and you can garble NAND gates, and therefore any arbitrary circuits can be garbled. So this is what happens in the classical world, and what we do is extend it to the quantum setting. It's a bit surprising that it wasn't defined before, but the first thing that we do is define a quantum notion for randomized encoding. And the definition is sort of inspired by the classical definition. Let me just point out the differences. So again, we have a quantum functionality. So we consider any functionality that is quantumly computable. It can have measurements, it can have trace outs, whatever you want, and it can be applied to an arbitrary quantum input, X. And again, the randomized encoding takes the input, it takes additional randomness, and here we also allow to take an auxiliary quantum state. And this we need in order to properly define this notion of decomposability that I mentioned before. So we also allow an additional quantum state as an input to this quantum randomized encoding. But again, you have the decodability property and the simulation property that are defined sort of in an equivalent manner. One thing that is important to notice in the quantum setting in particular is that definition needs to be robust also to the existence of auxiliary input. So we said that our input X can be an arbitrary quantum state, doesn't have to be a pure state, can have an arbitrary density matrix, but we also can consider a case where X is correlated with some other quantum state Y, and we want the correctness and simulation to also hold even in the presence of this arbitrarily correlated additional quantum input or quantum value. It's not an input. So this is the definition of quantum randomized encoding. And once we define it, we want to construct it. So we present a construction for quantum garbled circuits or decomposable quantum randomized encoding with gate-by-gate encoding. So our construction actually has two flavors, one with perfect security and one with computational security. And both of these are achieved in exactly the same way. You just need to sort of switch one component from sort of a perfectly secure component to a computationally secure component from literature. And let me sort of go over some of the properties of these quantum garbled circuits. So first of all, what is the complexity assumption that we need? So for perfect security, it's unconditional. We don't need any assumptions. For computational security, we need quantum secure one-way functions. And trying to compare it with the state of the art in the classical regime, we see that this is the same also classically. Now let's talk about the complexity of the encoding, so the complexity of computing this f hat function. And similarly to what we saw in the previous example, we can do this in constant quantum depth. However, there's a subtlety here, because usually in the classical setting, when we think about taking a fan out, we just consider fan out to be depth 1 or constant depth. Whereas in the quantum setting, it's not so clear whether we should allow fan out to be constant depth or not. We do require, if we want to argue that we encode in constant depth, then we also need fan out gates. So this is this complexity class QNC0 fan out, and this is the complexity class where our encoding lies. So it's constant depth, but it requires fan out. In terms of the size of the encoding, so let's start with the computational setting first. So the size of the encoding, if I'm encoding a circuit, if I'm garbling a circuit which has size S and depth D, then the size of the encoding is going to be polynomial in the size of Fs, and in lambda, which is the security parameter. So security parameter is a very basic notion in cryptography, which essentially quantifies the amount of power that our adversary has. So just for example, when you hear someone say a crypto system has 128 bits of security, this actually means that the security parameter is 128. So this is what this security parameter means. So here we just get something that's polynomial in the size and the security parameter. However, in the case of perfect security, again, we're polynomial in S, but we can also be, in general, even doubly exponential in the depth of the original quantum function f. And this is in particular curious when you compare it to what's known classically. So again, classically, you can get garbled circuits in constant depth. The size of the encoding is comparable in the computational setting. But if you want perfect security, then you can get it with only single exponential size in the depth of the circuit. And it's not clear whether this discrepancy is inherent. I mean, we try to do this in 2 different ways, and we end up with this double exponential factor. But it's still not clear to us whether it has to be the case or not. So there's something here to think about for future work. In terms of decoding, the decoding is of course not going to be shallow. Somewhere we have to sort of have a deep computation. But in terms of the total complexity, it's going to be linear in the size of the encoding that is produced. And simulation and encoding, and the complexity of simulation is the same as the complexity of encoding. So this is what we get in terms of the sort of complexity of the encoding itself. And another useful property that we have, well, I said that the input X can be an arbitrary quantum state, but it could be that a part of it, or even the entire thing, is classical input. And what we have, remember that we have this decomposability property. Each input bit or qubit can be encoded separately. And if this bit turns out to be classical, then the encoding procedure is also a classical procedure, which means that the encoding of the input for classical inputs is actually looks the same as what you get for classical garbled circuits. So it's just going to be a classical string that encodes this input bit. And this is also useful for applications. So this is one thing that we show. We also show in the paper an alternative construction. So this construction does not have, it's not a garbled circuit in the sense that it does not have a shallow encoding. It's not a gate-by-gate thing. And it's not decomposable. However, the overall structure of the encoding is somewhat simpler, and turns out it's kind of useful because there's already follow-up work that uses this in order to achieve better round complexity for quantum multiparty computation. The last thing that we show is an example of an application. So we show, well, in the spirit of this session, a zero knowledge protocol for QMA. And this has the form of a Sigma protocol. So let me sort of take you back to Alex's talk from the morning. So what we get is a protocol that has a similar structure to the protocol of Broadbent and Grilo that Alex showed in the morning, but it has some favorable properties. Well, in particular, for those of us who don't know how to do these sort of hard Hamiltonian reductions, this allows you to sort of get a good zero knowledge protocol without needing to do hard reductions. So this is just an example of an application that you can get, and you can get it very simply by just taking a well-known classical protocol and sort of substituting the classical garbled circuit for a quantum garbled circuit in sort of the right way. So you need to sort of be careful a little bit on what you do. So this is what we do in this work, and I want to tell you a little bit more about this alternative construction just because it's simpler to present. So this is what we're going to do next. So what we want to do is the following. So we want to take, we want to show for an arbitrary quantum circuit, we want to show that that any quantum circuit can be encoded in the following way. So you take the input, possibly add to it some auxiliary ancilla, which is sort of just a fixed quantum state. Pass these things through a random Clifford. So you just take sample a random Clifford and run the input through this. And in addition, I'm going to give you some classical side information. So this is sort of the process of the encoding. The output of the encoding is going to be sort of this output here, the output of this running the Clifford, plus this additional classical information. So this is sort of very simple structure for a quantum functionality. And we want to show that any quantum functionality can be encoded in this way. So we're going to start with a warm-up. So we're not going to go to arbitrary quantum circuits, but we're going to look at Clifford, which are, well, usually much, much easier for many of these type of applications. So it's not surprising that this is our warm-up. So we start with the Clifford G, and so this Clifford G that takes an input X and produces an output Y, which is G times X. And let's try to encode it in sort of something that looks like this. So what we're going to do is we're going to sample a random Clifford. So what the properties of Clifford that I'm going to use are, so we know that we can efficiently sample a random element or a random circuit from a circuit that computes a random element from the Clifford group with a given input length. So this is what I'm going to do. I'm going to sample one of those random Cliffords, and I'm going to pass my X through this random R, and I'm going to get Rx here. And in addition, we're going to use the property that for Clifford circuits, we can actually come up with a canonical representation. So if I give you some Clifford circuit over, let's say, n bits, you can come up with a representation of the same unitary, the same functionality, but with one that does not reveal the original implementation that I gave you. So I'm going to give you a canonical representation of G times R inverse, and I'm going to call this value S. Now let's see why, if I give you R times X and this S, this constitutes a randomized encoding of my original function. Well, first of all, notice that it can be decoded just by taking the circuit S and applying it to the value R times X. This is going to give me G times R inverse times Rx, which is just G times X. So this is good. The decoding property is going to hold. Now for the simulation, we notice that the marginal distribution of this S is just a random Clifford. G times R inverse, since the Cliffords are a group, G times R inverse, the marginal distribution is just a random Clifford. So when we want to simulate, what we're going to do is just take S to be a random Clifford. And in order to simulate this part of the encoding, we're just going to take S inverse times Y. I don't want to get into the details, but you can notice that this actually is distributed exactly the same as the original encoding. And lo and behold, you did get exactly this form that we wanted. We didn't even need the auxiliary information for the case of Clifford. So this gives us what we wanted. And an important feature of this example is that it hides the original circuit G. What do I mean by hiding the circuit G? Well, intuitively, it means that when you get the randomized encoding, you can compute the output, but you don't even know which circuit, you don't get any information about the circuit that was used to compute this value, not just any information about the input, but no information about the circuit as well. And formally, this is formalized by this sort of property that we saw, that in order to simulate, you don't actually need to know what G was. So this simulation that I sort of very, very roughly sketched does not require knowledge of the original circuit G. Okay, good. So this was a warm-up. Now let's sort of try to get to the sort of real business. We want to get the structure for an arbitrary quantum circuit. So again, I'm sort of being kind of lazy and considering a restricted class of circuits. Now it's going to be circuits that have Clifford plus measurement. What is this class? So it has this following structure here. So the input is going to consist of a multi-bit input X and an additional qubit B. And these can be arbitrarily quantumly correlated. The circuit, what it does, the first thing that it does is measure this qubit B. And then based on the output of this measurement, it applies one of two Cliffords, either Clifford G0 or Clifford G1. So this is more complicated than just Clifford, but it still seems fairly simple. So you can think that maybe this is another warm-up. But no, actually, if you manage to do this for this Clifford plus measurement class, then you can use this magic state mechanism of Bravia and Kitaev and sort of apply this recursively and actually get a quantum randomized encoding of this form for any quantum circuit. I don't want to get into the details. Just I just want to say that this is actually going to be sufficient for us in order to get the general case. All right, good. So this is sort of a well-defined task. Let's try to see how to do it. And OK, so we have not just one Clifford here, but two different Cliffords. Let's try to do similar things to what we did before in the warm-up. So I'm going to sample a random Clifford R again, and I'm going to run my X through this random Clifford. But now, before I gave you this S, which was G times R inverse. Now I want to give you either G0 times R inverse or G1 times R inverse. And which one of the two I'm going to give you is going to depend on this measured bit B. So notice that by exactly the same argument that we saw before, if I give you the output of this R times X and either G0 R inverse or G1 R inverse, not both of them. So remember, this is the classical description of a canonical classical description of the circuit that computes this, this unitary. So if I give you one of these two, the appropriate one, plus this R times X, then you're going to be able to decode. And this is also going to be simulatable in a very similar way to what we saw before. Good. So this part looks good. This looks like what we wanted. Let's zoom in on this part and try to sort of massage it so that it also looks similar to the form that we wanted. So we have a measurement and then a selection between S0 and S1. So the first thing that I'm going to do is just run this thing coherently. So rather than first measuring and then doing the switch, I'm going to consider a Clifford circuit that starts with B comma 0 and then computes in this ancilla register the value G sub B times R inverse. And since I can, if I'm allowed to hard code S0 and S1 into my circuit, then I can do this very simply using a Clifford. And then I can just measure everything, and I'm getting exactly the same functionality as I got here. So far, we have an identical functionality, but we still have this annoying measurement, which is not a Clifford and not even unitary, that we need to get rid of. And this we can do using the Pauli Z-twirl. So it is known that applying a measurement is actually equivalent to applying a random Z-gate, so either applying Z-gate or not applying Z-gate at random to each one of the qubits independently. And this is what we do here. But actually, there's sort of a nice perspective on the Pauli Z-twirl that you can. I mean, this is sort of a well-known object from the literature, but you can also think about as a randomized encoding. So what we actually show here is that what's actually true here is that the measurement functionality can be randomly encoded by some family of some distribution over Cliffords. And so this is the property that we use. OK, good. So what we got here is that this thing that has measurement and selection and so forth. Now we show that this can be encoded by some distribution over Clifford. So this is a Clifford. This is a Clifford. These things, it's a distribution because it depends on the randomness that we used. But it's still just going to be a distribution over Cliffords. So let's plug that back in. So what we get is that now our encoding looks like sort of a tensor of two different Cliffords. This one is random, and this one, well, it's not random, but it relies on some random values that we computed. The tensor of two Cliffords is also a Clifford, so we can just use our group randomizer, what we saw in the previous slide. If we just have an input that goes into a Clifford, then we can convert it into this form, just as we saw before, and we're going to get some classical information that depends on the original circuits, G0 and G1, and on the random values, capital R, small r, and r prime. So this gets us to the form that we wanted. And I just wanted to point out that along the lines of this encoding, we had to compute some classical functions. So there's this auxiliary input f, And also these S0, S1s require some classical computation in order to sort of compute their canonical representation. And if it's too hard for us to do during the encoding process, then we can just use classical randomized encoding and sort of, instead of computing these things by ourselves, compute the encoding of these values and leave it to the decoder to actually sort of figure out what the actual value was. And this helps in reducing the complexity of the final encoding that you get. So this is I'm back. So this is the construction that I want to show today. And to wrap up, let me just sort of very briefly sort of mention just the classes of applications that we hope or we expect to have for these things. So as I said, this notion of garbling and randomized encoding is very useful in classical cryptography. And one thing that you can try to do is take these known applications of garbled circuits and sort of plug quantum in front of it and see if it makes sense and if it sort of gives you some advantage. But maybe you can also think of new quantum applications, new cases where randomized encodings can be used in the quantum setting, which don't have a parallel in the classical world. So this is sort of quite open-ended. We have seen already some follow-ups or some applications in the context of quantum secure multiparty computation. There's this application for privacy mutual messages that I don't have time to go into. And one interesting direction that you may want to go to is try to get program obfuscation, which is sort of extensively studied in the classical regime now and seems to be related to the notion of randomized encoding. And maybe you can try to use these techniques for achieving quantum notions of obfuscation. Thank you.
Big round of virtual applause. We have a question in the chat in the Slack channel. It's coming from Sagnik Chatterjee. And it goes is the following: a naive question. Does the randomized encoding complexity, perfect security case, imply any meaningful separation between QNC0F and NC0?
You're saying because in QNC0F you can encode arbitrary quantum functionalities. So I would be interested in a little more details on why this would imply a separation. You're saying so to derive. So if you had a separation from maybe a conditional separation based on a separation from BQ, P, and P. I'm not sure. I mean, I'd be very interested to see how this would work.
Okay, due to the fantastic technology, we actually can't have it back and forth question period, but you can go after, just as a reminder, to the roundtable. That'd be fantastic to follow up on that. Question from Zhu Cao. Can we get rid of the fan-out gate in QNC0F?
Yeah, we really want to. It seems like it would be hard because even for classical garbled circuits, you need fan-out. So it seems like some fan-out is needed. However, we did try to think whether we can sort of only rely on classical fan-out. So maybe sort of try to explain why the fan-out that we need to use is sort of the mildest form of fan-out that could possibly exist. Like why it's really not more complex than classical fan-out. We don't have a meaningful way of reasoning about it, but I'm hopeful that maybe one does exist. So, I mean, it is interesting to sort of try to pinpoint why you need QNC0 fan-out, or if you need some milder class. I guess I should say maybe that the number of fan-out gates that we need is, I guess, the fan-out depth that we need is 2. This is more restricted than like arbitrary constant depth fan-out.
Okay, let's give it a few seconds in case there's some last minute questions. And maybe the next speaker can get ready in that time. Okay, thanks again, Zvika.